Continuing with logarithms, we need to investigate exponential growth and decay and look at California State Standard number 12. We need to know the laws of fractional exponents, understand exponential functions, and we've covered that. But to finish it out, we need to use these functions in problems involving exponential growth and decay. So our objective is to use exponential and logarithmic functions to solve these kinds of problems, growth and decay. Here's the formula I would suggest using for growth. I prefer this one over the textbook. And I know we have uppercase N equals lowercase n times e to the kt power. As we learned previously, e is that constant of growth. Now, to explain this formula, what we have is the lowercase n is the initial amount, the amount we're starting with. And when things are growing, we're starting with a smaller amount, and we're ending up with a larger amount, so capital N is the final amount, which should be larger for a growth problem. So I like to use lowercase and uppercase n because it helps students understand what's the beginning initial amount, which is smaller, what's the final amount, which is more. So E is that irrational number that we learned in section 8. K is the constant of growth, how fast things are growing, and T is time, which could be measured in seconds, minutes, hours, days, years. So let's look at an example. For a certain strain of bacteria, the constant is 0.775 when T is measured in hours. How long will it take for 2 bacteria to increase to 1,000? So let's start with our exponential growth formula. The final amount, capital N, is equal to the initial amount, lowercase n, times e raised to the kt power. E is that exponential growth and decay number. To substitute in what we know the initial amount is 2, starting with 2 bacteria, ending at 1,000 bacteria. We know the constant is 0.775. The only thing we don't know is t. And so we need to solve for t in this equation. Now, to make it easier, I suggest let's try to isolate e and its exponent. And let's do that by dividing both sides of the equation by 2. When we do that, we have 500 equals e to the 0.775 t power. And we learned our laws of exponents. And there's only one thing that can get the exponent and turn it into a product, and that's taking the log of both sides of this equation. Instead of base 10, because we have e here as a base, we're going to use our logs base e, or the natural logs that we covered in section 8. So we're going to take the natural log of both sides of the equation, and it looks like this. Natural log of 500 equals the natural log of e to the 0.775 t power. When we do that, you type 500, hit the natural log button, we get 6.2146, round it to 4 places, hit the clear button on your calculator. When you have the log of any number raised to a power, our law of logs said that's the same as that exponent times the log of that number. And here's the nice thing about taking the natural log when we have e. The natural log of e is always 1. Natural log is base e. And we're saying e to what power is this e to the first power? That's 1. So the nice thing is that always turns into 1. And all we've got to do is divide both sides by 0.775 and we'll have t and we'll have our answer. So to do that, just change the sides of the equal sign. Some of you like to see the variable on the left. Divide both sides by 0.775. Round my answer to 4 decimal places. But in this case, we can probably get away with the nearest hour here. But we'll look and see what the directions say. So yes, it takes approximately 8 hours for this certain type of bacteria for 2 of them to grow and increase to 1,000. Which I guess explains why you can go to bed feeling great and the next morning when you wake up feeling sick. You've got that bacteria growing in an exponential pattern. That will certainly explain it. Well, let's look at our formula for decay. And I pretty much use the same formula. The only difference you'll notice is I switch places with the lowercase n and the capital N. But still, on the right side is the initial amount. And on the left side of the equal sign is still the final amount. But for decay, we're starting with something larger, so the uppercase n here, and we're ending up with something smaller, lowercase n. E is still that exponential value and constant from less than 10/8. K is the constant of the decay in this case, and it should be a negative number. And here's where I differ with the book. The book works this formula in a different way, that K turns out to be a positive number. So I would suggest stick with the formula that I'm using here. T is still time. Can be anything from seconds to years. All right, so let's look at our first problem. In 10 years, a mass of 200 gram sample is reduced to 100 grams. Now, that's called half-life. Whatever you start with is your initial amount. Your final amount is half of it. And in this case, we're just doing a one-step problem. Find K, the constant of decay. So let's start with our formula for decay. Lowercase n for the final amount, because it's smaller, equals uppercase n for the initial amount, because the initial amount is larger, times e raised to the kt power. Fill in everything we know. Final amount is 100, initial amount is 200, time is 10, e is a constant, it's not a variable, so we're solving for k. To do that, it'll be easier if we can get e by itself. So let's divide both sides of the equation by the 200 to undo multiplication by 200. And we get 0.5 is e to the 10k power. Again, we have base e. So natural logs is our natural response to take the natural log of both sides. So take the natural log of 0.5 on your calculator, you get negative 0.6931. On the right side of the equation, the log of a number raised to a power is the same as that power times the log of the number. And the natural log of e is 1. Natural log is saying e to what power is e to the first power, and that's 1. To get k by itself, I'm just changing sides of the equal sign. Divide by 10, and we found the constant of decay here is negative 0.06931. Now we did that as a one-step problem, but quite usually we have a two-step problem when we're looking at decay. So let's look at example 3. It says there's an isotope of a synthetic element called californium. And no, I'm not making that up. There is actually an element, californium. No joke. So it has a half-life of about 45 minutes. How long would it take for a given sample to decay and lose 85% of its mass? Now this is a little different because we're talking percentages. You're saying, what's the original amount? What's the final amount? So here's our strategy, kind of small. The problem requires two steps. First, you want to find the constant of decay, which we represent by k, since that's not given. And we can start with anything as our initial amount. This is half-life. So our final amount is going to be half of it. We can start with 2 and end with 1. We can start with 1 and end with a half. And we're going to solve for k. That's step 1. Second, since we're talking percentages, let's start with 100 grams as our initial amount. And then our final amount is 100 grams minus the 85, which gives us 15 grams. So that's where we're headed. Let's start with our formula for decay. Let's substitute in what we know. It's a half-life. Doesn't matter what we're starting with, our final amount is always half. And it might be you could save a step. Instead of starting with an initial amount of 2 and a final amount of 1, you could start with an initial amount of 1 and a final amount of a half. Okay, the other thing we know is t is 45 minutes. So we need to find k as our next process. So let's divide everything by 2 so we can get e by itself. So 1/2 is e to the 45k power. We could have got there as our first step if we said our initial amount was 1 and our final amount was a half. Since we have e as a base, we're going to take the natural log of both sides. You're going to see the natural log of a half quite often in half-life problems. So that's still negative 0.6931. Log of a number raised to a power, that property says that's the power times the log of the number. The natural log of e is still 1. And I'm just going to change sides of the equation. 45k is negative 0.6931. To find k, let's divide both sides of the equation by 45. And let's round this to 4 places. And clear our calculators. Round it to 4 places. So then our constant here is negative 0.0154. But that's not what they asked us. The question was, how long would it take to lose 85%? This is half-life. That's losing 50%. But we found the rate at which it decays, the constant. So for part 2 of this problem, our initial amount, let's start with 100 grams of this element, because we're talking percentage, and percentage is out of 100. We're losing 85%. So we're losing 85 grams. 100 grams minus 85 grams is 15 grams. Times E, and we solved for K, so that's still negative 0.0154 times T. Now we're looking for T. To get E by itself, let's divide by 100. And we have 0.15 on the left is equal to E to our constant times our time. To get rid of this variable, take it out of the exponent and turn it into a factor, we're going to take the natural log of both sides. Natural log of 0.15 is negative 1.8971. The log of a number raised to a power is that power times the log of the number. Don't forget the natural log of E is 1. And if we divide by negative 0.0154, we will find out what T is. And if we round that, that's approximately 123 minutes. So just look for the directions to see if we want it rounded, or 4 decimal place accuracy would be 123.1883 minutes. All right, let's look at another kind of growth. And this is one we call compound interest. You learned simple interest in Algebra 1 or before that. That was interest equals principal times rate times time. This formula, P is the principal, amount of money you're investing or borrowing. R is the interest rate, and that's a percentage, so that's out of 100. N is how many times we're going to compound that interest a year, how many times we're going to calculate it. Simple interest assumes it's once a year, but it's not that case. T is how many years, and A is the final amount you have in the bank, or the final amount of money you owe for whatever you borrowed, for car or house or whatever. And we don't have I here, how much interest. But we can find interest because interest is always the final amount minus the initial amount, which is principal. But again, it's very similar that on the right side of the equation, P is our initial amount, what we're starting with, our principal, how much we're investing, how much we're borrowing. A is the final amount, which is the principal plus the interest we're getting. In this formula, that's the number 1, in case you couldn't tell. Plus R divided by N. R is the interest rate. N is the number of times the interest is compounded per year. And that quantity is raised to the NT power. N is still the number of times we're compounding the interest per year. T is the number of years. So let's apply that to a problem. How long will it take an investment of $1,000 to triple in value if it's invested at an annual rate of 12% compounded quarterly, which would mean 4 times a year? Let's start with our formula. Let's fill in what we know. If the initial amount's 1,000, we want it to triple. So our final amount is 3,000. 1 is 1. Interest rate is 12%. That's out of 100. So 12 divided by 100 is 0.12. N is 4 because it's compounded quarterly. That's 4 times a year. All right, that'll become more easy if we divide both sides by 1,000. Get this parentheses by itself. So 3 is equal to 1 plus, and 0.12 divided by 4 is 0.03 raised to the 4t power. 1 plus 0.03 is 1.03. We're going to raise that to the 4t power. And there's only one thing that can take an exponent and turn it into a factor instead of an exponent. And that's taking the log. And you might say, wait a minute, what happened to natural logs? Well, I didn't have base E. That's when I really want to use natural logs, when we have base e. So in this case, I'm going to use base 10 logarithms, and that will work just fine. So the log of 3 base 10 is 0.4771. When you get the log of a number raised to a power, that's the same thing as the power times the log of that number. We'll look up the log of 1.03, which turns out to be 0.0128. Multiply that by 4. And then we will divide both sides by 0.0512 to find out what t is. And when we do so, our answer is 9.3184, or we can say approximately 9.3 years. So if you found an investment at 12%, compounded 4 times a year quarterly, your $1,000 would become $3,000 in approximately 9.3 years. That's our look at growth and decay formulas for today.